Hello, and welcome to this Vivado quick take on a popular and important time enclosure topic, physical optimization. What if you had an option to let the tools run a little longer and in return, possibly get better design performance? That's physical optimization. In this quick take, you'll gain an understanding of how physical optimization is used for time enclosure. In particular, what do we mean by physical optimization in Vivado? What kind of tool feature is this? Also, when is it used? Should it always be used? Why or why not? And if it is used, where does it fit in the design flow? And finally, what does it do to improve design performance and therefore help close timing? Faster time enclosure is really the ultimate goal. Before we get started, this training assumes that you're already familiar with the implementation flow. If you do not already know how to place and route your design, we recommend you first watch the Vivado Design Flows overview video, which gives a good introduction to some key concepts we cover in this video. Those topics include working with and without projects, basic design flows including implementation, and using Vivado tickle commands. Another good quick take to see is the one on implementation directives and strategies, since we will also be talking about strategies. Okay, here's how we will tackle physical optimization in this quick take. First, as promised, more details about physical optimization, some background to gain a basic understanding. Then we'll show you where you can find and access physical optimization in Vivado, whether you're working with projects or a non-project mode. And finally, we'll conclude with some examples showing the benefit of improved timing with physical optimization. Physical optimization in Vivado is a tool feature that applies a collection of techniques used to improve design performance after placement and after routing. The fundamental principle behind physical optimization is that certain logical optimizations such as fan-out replication are more effective when performed with physical data. Take for example a case of a timing violation on a net with multiple fan-outs. Although replication could be done logically, the choices of how to divide the loads and how much logic to replicate is somewhat arbitrary. But after placement, these choices become more concrete based on the placement of the drivers and their loads, and their estimated delays, which are more accurate because location is taken into account. Optimizing physically results in the right amount of replication in the right locations, which is more effective and more efficient than purely logical replication. Another important aspect of physical optimization is that it involves no manual operation. It automatically updates the net list, places cells, and even routes nets when needed to create a fully legal design. From now on, in this quick take, we're going to refer to physical optimization by its well-known abbreviated nickname of PhysOpt. So, what optimizations are included in PhysOpt's bag of tricks? As you can see from this table, there are a vast number of optimizations ranging from replication to retiming to purely physical operations such as placement and routing improvement. There are far too many to cover in detail in this quick take, so please see the implementation user guide UG 904 for more details. Also note in this table there are two columns, one for post-placement and one for post-routing. PhysOpt actually operates in two different modes depending on whether the design is fully placed or fully routed. Not all optimizations are included in both modes, as optimization in one mode may not be suitable for the other. But this is subject to change and there is always a possibility of new optimizations coming online. Let's take a look at PhysOpt in Vivado. Here I have a netlist project, and we'll go to Implementation Settings, where you can see PhysOpt in the flow. Under Options, we see the implementation flow steps like Opt Design, Power Opt, and here we have Place Design. After placement, you can see Post Place PhysOpt Design, and here's a checkbox to enable it. A little further down, we have Route Design, and after that is a Post Route PhysOpt Design step, and the checkbox to enable it. At this point, you may be wondering, why isn't PhysOpt enabled by default? Why do I have to enable it? Well, the primary reason is that PhysOpt does require some tool runtime, and Vivado tries to optimally balance runtime and design performance, so it is off by default. But if you can tolerate some extra runtime, this is a very easy way to get a performance boost. So, don't forget to enable PhysOpt if you think you need it. Another thing to note is you can use directives with PhysOpt. Under the directive setting here, you can see the various directive names that choose different goals and algorithms to be applied. Also under the post-route PhysOpt step, you can see those available strategies. The available directives are also different between post-place and post-route. In parentheses is a tickle command PhysOpt design, which you would use in non-project mode or when working with tickle scripts. I'm going to cancel this pop-up and go to the Tools options. And here you can see the implementation strategies. Remember, PhysOpt is off by default, so the default strategy does not enable it, but many of the presets here do have PhysOpt enabled as part of the flow. All of the performance strategies here use PhysOpt, and there are some flow strategies that enable PhysOpt, the post-place and post-route. So another way to access PhysOpt is to just use a strategy that includes it. Okay, let's get back to the design. We have 3 implementation runs here. The first one did not meet timing. It's missing timing by about 300 picoseconds. For the second implementation run, post-place PhysOpt was enabled. You can see the results were better. The lapse time increased, but we got very close to meeting timing. Let's take a look at the log file. Okay, here is where placement finished, with an estimated slack of about negative 750 picoseconds. After placement, here is PhysOpt design. It begins with the same negative slack, and here you can see it go through the different physical optimizations, reporting progress, and then finally it brought the slack all the way down to just over negative 200 picoseconds. The router was eventually able to bring it all the way down to a 3 picosecond violation. You may ask why PhysOpt stopped short of meeting timing, and this is because, like Vivado as a whole, PhysOpt also balances runtime and design performance. You can try other directives and strategies that allow PhysOpt to be more aggressive, spending more runtime but also potentially getting even better timing slack. In non-project mode, you can even run PhysOpt successively, one call after another, until timing stops improving. In the third implementation run, we took things one step further and added the post-route PhysOpt step. Here PhysOpt was able to close timing with a positive 33 picosecond slack. Note that the command and syntax are exactly the same between post-place and post-route, still PhysOpt design. PhysOpt automatically determines which mode to use based on the design state. We don't have time to cover all the optimizations in this quick take, but we'll take a detailed look at a couple of the many optimizations performed by PhysOpt. The first one, called critical cell replication. You can think of critical cell replication as a form of low fan-out replication, where a cell that's in a critical path is replicated to improve delay. Here's our design for this example. After synthesis, timing was met, but after placement, we have these timing violations. If we take a look at the critical path schematic, here's what it looks like. From a logical standpoint, it's not completely obvious how to improve the timing, other than possibly refactoring the RTL. Next, we're going to run PhysOpt design and specify the -critical cell opt switch. And by using this switch, we limit PhysOpt to performing critical cell replication only. After PhysOpt runs, we get a positive slack. Let's take a look at the critical path now. Going back to the schematic, take a look at the first LUT in the critical path. PhysOpt replicated this, and the copy of the LUT was used for the critical path, which now meets timing. Here's what the placement looks like now. You can see the copy was moved closer to the destination logic to get a better placement and fix the timing violations. One more optimization that we'll cover is forced net replication. Recall PhysOpt is timing driven, and sometimes timing estimates can be optimistic, particularly for high fan-out nets. The optimization of forced net replication can be used to replicate a driver regardless of its timing slack. If we run report high fan-out nets with a -timing switch, we can see the slack for the nets with the highest fan-out. Now let's just say for the purpose of this example that this particular net driven by this 2-input LUT with fan-out of 1017 violates timing after routing, and we see that the slack before routing is positive by about half a nanosecond. In this case, post-place PhysOpt is not going to replicate this LUT driver because it's not in a critical path. If we take a look at the placement, I have a script here that highlights the nets. The yellow nets are the 2 LUT inputs, and the green net is the LUT output. The loads of the LUT are fairly spread out. Then we call PhysOpt design-force replication on nets, and we give it the green net, and PhysOpt goes to work replicating the LUT driver. After replication, I have another script here that highlights the changes. We now see that the green net and its driver have been replicated several times, with the resulting drivers placed closer to their loads. For this option, there's no fanout limit such as a max fanout value to specify. PhysOpt automatically replicates based on the placement. After forced net replication, you can run PhysOpt again on the replicated nets to even further reduce the fanout loading if necessary. Now, there's some important rules to keep in mind when using PhysOpt. PhysOpt is timing driven, therefore it works on critical paths that violate timing constraints. PhysOpt does nothing if there are no timing violations. PhysOpt does not always work on all the timing violations in the design, only the most critical. Use directives such as explore to perform more aggressive optimization. PhysOpt is reentrant like other implementation commands, meaning that you can run PhysOpt repeatedly on a design to try to improve timing iteratively. PhysOpt performs only some optimizations by default, and you can control which optimizations to run using command options. So to wrap things up, physical optimization is a collection of timing-driven optimizations you can run in Vivado to improve design performance for faster timing closure. It can be run post-placement, post-routing, or both. Remember that PhysOpt is off by default, so you do need to enable it in the implementation settings if you're using projects, or choosing a strategy that uses PhysOpt such as the performance strategies, or by just calling the PhysOpt design typical command at the command prompt or in scripts. Remember that PhysOpt is a powerful, effective, and easy to use timing closure technique. For further information, see the other quick take videos, the Vivado design flows overview, and the implementation directives and strategies. PhysOpt is also covered in the implementation user guide, which is UG 904, and if you're working in Vivado, just type PhysOpt design-help for a complete description of the syntax and usage of the PhysOpt design command. This concludes the Vivado quick take on physical optimization. Thank you for watching.